All right, we're going to try an exam style question, a conceptual one, asking about how the rate constant changes with changes to your reaction. So basically, what does the rate constant depend on? So let's remind ourselves, let's give ourselves some background on the rate constant. Remember, we started out by writing that rate equals K and then times concentration of our reactant to some power, and maybe times the other reactant to some power. Okay, and so this gave us the connection that the rate of the reaction depends on concentration. And in class, we all felt fairly comfortable with that connection. You have more reactant, that means there's more reactant to react, so it should be faster, right? If you have 100 things and like you're waiting for one of them to change into a product, it's more likely that something will change into a product than if you're just waiting for one thing to change. I don't know if that analogy landed, but that's how I think about it. And so there's our connection between rate and concentration of reactants, right? It's right there in the equation, okay? K is outside of that. K does not depend on concentration. K incorporates or like enfolds all of the other variables that change or have an impact on a rate's reaction. Okay, so we named those in class. We said there's the physical state. We're going to tie this to the collisions or number of collisions and percent success of collisions. And that is connected to the orientation factor that we talked about. How likely is it that any collision is going to result in a reaction? That's going to depend on how big the molecules are. If you were just waiting for like maybe I and I, so like two iodines, like they're going to make a bond. It doesn't matter if they hit this way or if they hit that way or this way, like they're symmetrical all the way around. So any collision presumably will result in a reaction provided there's enough energy. And there would be in that case. But anyways, that's aside, little tangent here, versus like, say you are looking at this and you really need, here's your, 3-atom molecule and you're reacting with this other one, and we have to have a connection between these two. So like you could hit here and here and here, and all those might be successful, but if this other atom hit in any of these other spots, like that's not going to work, right? So that is going to have a role in how fast the reaction goes, and that's folded into K, and that's our A. So this is, all of this gets folded into A, big A, which is our frequency factor. All right, K depends on that. K also depends on the activation energy. All right, that's EA. And that's just like how big is the hill in front of the reactants, okay? So the activation energy is from the reactant energy all the way up to the transition state. So the highest energy point. Where is this thing the least stable? You're starting to break bonds and you haven't got the payoff of making the new bonds. You're in this like middle ground where nothing is optimized. And so you have a really high energy. That's EA. Okay, and K depends on that. That makes sense that this should impact the rate, so that better be folded into K as well. So big, we'll just make the comment big EA, small K, which would mean a smaller or slower rate. A small EA would mean a big K, which would mean a faster rate. And then lastly, we have temperature. We know that that is also an important factor for rate. If you increase T, the rate goes up, which mathematically means that K is going up, okay? So those are our three factors. Arrhenius put those together to say that K equals A, our frequency factor, times E to the negative EA divided by RT. So there's K. It depends on this like physical state, like the number of collisions, the success of those collisions. It is a kind of catch-all term. It's got a lot in there and it's kind of hard to interpret. We have the activation energy. That's not hard to interpret. We know what that looks like on the graph. We know that that's how much energy needs to be put in to get over the hump. And then we have temperature, right? And temperature increases the number of collisions because our particles are just going so fast that they're more likely to run into each other. But also when they do hit each other, when they have At higher temperature, they're likely to have more kinetic energy, which means that they're more likely to make it over that activation energy barrier. All right, so that's all the things that K depends on. Now, finally, I'm sure you're just like, can you answer the question? So this is, how does the rate constant K change with each adjustment? All right, so when the temperature is decreased, K decreases. It gets smaller, okay? And you could prove that to yourself mathematically. You could try changing the temperature and seeing what happens to K, but it's gonna go down. When the activation energy is lowered, okay, so when we have a smaller barrier, K should increase because it's gonna get faster. So we must have a bigger K value. Here it would have been slower. And then lastly, we ask, how does the rate constant change when the concentration of reactant increases? And this is no change. Because K does not depend on concentration. The rate does, right? We see that relationship here, but K does not. That is, I think, you have the intuition for it, but then a lot of students, I see this as a very common error on the exam, that they're tricked into answering that that's going to have an impact on K, and it doesn't. So write down these equations, look at them on your equation sheet, be like, K does not depend on concentration. I'm not going to answer that there is a connection between K and concentration, okay? You're not going to do that. This is your reminder.